Today, this is physics for class 12. Physics for class 12. Here, this is electromagnetic waves. Electromagnetic waves. Electromagnetic waves, and I am dealing today with the displacement current. Displacement current. Here with the displacement current. Here you see that from Ampere's law, your Ampere's law, it is that cyclic integral of B dl is equal to nu naught I. It is the current flowing through the loop. Suppose this is the current flowing through the loop. This is the current flowing. Here I current. This is the I current flowing. And if we want what will the magnetic field here, so we draw an Ampere loop here and its radius be r. So we draw an Ampere loop here. So the magnetic field at this point B, according to Ampere's law, that will be cyclic integral of B dl, that is equal to nu naught I, and here B cyclic integral of dl, that is the 2 pi r. So this will be nu naught I. So your magnetic field here will be nu naught I by 2 pi r. This will be your magnetic field. Now here one thing come here that this is one point. The second point, change in electric field, gives rise to magnetic field. Change in electric field. Your change in electric field gives rise to magnetic field. Change in electric field gives rise to magnetic field. So now the change in electric field gives rise to magnetic field. For this concept, we are considering an capacitor. For this concept, we are considering a capacitor. So here, this is a capacitor, and plus, and here this is minus, and the current flowing through this. This current is a function of time. Current flowing through this. This is the function of time. So now we have considered three cases. So this is the first case. Let me draw this side. So there are three cases. The first case is that this is a capacitor. We are taking a capacitor and a current is passing through it. This current is a function of time. So here, this is one case, and so here we want to find a magnetic field at the point, say P here. We want to find a magnetic field at point P outside the plate. So here we are going to draw a loop, circular loop, and it is that it will be a radius of r. So magnetic field at P, your magnetic field at P will be, according to Ampere's law, this will magnetic field B is equal to nu naught I, function of time, by 2 pi r. So this will be the magnetic field at point B. Now another case, second case. In this case, considering this opening, we draw a pot Here this is a pot. Considering this is an opening, we can pot, and this face is in between the two plates. The bottom of the pot, the bottom of the pot, this is a pot. Pot is in between the two plates, and this pot is not connected to the current. It is not connected. It is not connected to the current. It is not connected to the current. This is a second case. Keeping this opening, this loop, keeping this opening the same, we construct a pot here. And the third case is here. The third case is here. Third case here is, this is the third case. The third case here is I, function of time, and keeping the same opening, the opening is same. We consider in here a tiffin where its base is open, where this base is open. Here this base is, we considering a tiffin, and this is also, it is not connected to the current I. So here you see at point B, since the pot it is not connected with current I, so the magnetic field at B, here your magnetic field at P, magnetic field will be 0. And again here at the same point P here, the same point, because this is not, it is not connected with this current I, so here also at magnetic field at P will be, magnetic field will be also 0. So what we find that the methods are different, but at the first case we find a magnetic field here P at P, but in the second and the third case the magnetic field is 0. So here a contradiction has arisen, because if there is a magnetic field at P, how can this magnetic field at the same point, same thing, how can this be 0? So irrespective of the method you have taken to calculate the magnetic field, everywhere there must be a non-zero magnetic field. Irrespective of the method you have taken to calculate it, the magnetic field at all this P must be 0, must be non-zero, So this is the very important point. The magnetic field at these are the same point, it must be non-zero. But what we have find that here the magnetic field, there is a magnetic field, but here this is the magnetic field is 0, and here also magnetic field is 0, because this pot is not connected with I, and here also this tiffin box is also not connected with I. So that means what is the problem? That there is something missing in the Ampere circuitry law. There is in Ampere's circuitry law, there is something missing. So we are going to find out what is the missing here. So here you see that there is something which is moving from here to here. What is it is moving? Here it is open. So here something is moving. What it is moving here? The electric field is moving. Electric field is moving here. So that means the electric field here is Q by A, your epsilon naught. This is your electric field. This is the field which is moving here. So here your flux will be phi is equal to E dot A. So electric field is this. So your flux comes to be Q by epsilon naught. Now you differentiate this with respect to T. This is your electric flux. You are going to get d phi E by dt. So that is equal to 1 by epsilon naught dq by dt. So this is the current. This is current. So here you what do you got? Phi E by dt into epsilon naught. This is the current I. And this current is called the displacement current. Displacement current. This is called the displacement current. This is the displacement current. So now the Ampere circuitry law, it will become like this, that is the cyclic integral of VDL. This will be equal to conduction current plus displacement current. Conduction current, that is the current flowing through this conductor, and your displacement current is this. This is called the displacement current ID. So this becomes IC, and this is epsilon naught d phi e and dt. So if you, from this, that is the, what do we get? From this we get at every point P, the magnetic field is non-zero, and the magnetic field at P and magnetic field inside here M, or magnetic field at P or inside this M, here the magnetic field will be the same. So this is called as Ampere's Maxwell law. This is called as Ampere-Maxwell. So this is all about the displacement current, and it is very important because this is asked in your board exam.